Okay, hi folks. My name is John O'Reilly. I'm based in Galway in the west of Ireland. I would normally also say at this point that I live on the western edge of Europe, but it turns out that Lisbon is just a little bit further west than Galway, as it turns out. I'm a Kotlin GD. I work remotely as a staff engineer for a company called Crank & Technology. They're based in London and are part of the Octopus Energy Group. The plan today is that we're going to go on a guided tour of various libraries used in a number of the Kotlin Multiplatform samples I've been working on, along with other folks over the last 5 years or so. Just to start with the usual show of hands, how many people here are using Kotlin Multiplatform? Okay, quite a few. And how about Compose Multiplatform? Okay, as expected, maybe a little bit less. I've been asking this question, by the way, in talks over the last 5 years. It's been fantastic to see the steady increase in people using it. Just to start with a tiny bit of background, I started taking an interest in Kotlin Multiplatform around the end of 2018. And I had at this point here just about got something very basic up and running using this Galway bus app project. This had just been an Android-only app at the time, and was in general a project I was using to try out new technology. Interestingly enough, the following day, June the 3rd, 2019, SwiftUI was announced at WWDC, and was available to try out straight away, which of course I did. Jetpack Compose had been announced at Google I/O a few weeks before that. And so began this amazing combination of declarative UI and Kotlin Multiplatform. And 5 years later, this is where I find myself with 11 KMP samples now, a number of them created in collaboration with other folks. So these samples cover use of a range of different architectures, remote access, persistence approaches, etc., and different libraries used for each of those in many cases. I'm not going through all of them, but we'll use a number of the samples to illustrate various patterns and some examples of how these libraries are used. By the way, I'm including links in various places so that hopefully these slides can act as somewhat of a reference for folks that want to look into them in detail at a later point. I'm going to use these specific 5 samples as a basis for our exploration today, illustrating use of the KMP and CMP libraries shown. These cover approaches for retrieving data from a backend, persisting locally, dependency injection, ViewModel component sharing, navigation, Swift Kotlin interop, packaging, and also include a number of Compose Multiplatform UI libraries as well. There's quite a few libraries here, so we won't go into great detail on each one, but we'll hopefully provide at least a flavor of what the library does and how it can be used. Before we get into details, I just want to give a big shout out to all the folks who have contributed to these samples over the years. In a number of cases, this was their first contribution to open source. By the way, these are the full set of libraries used in samples I have. We have a number of the standard JetBrains libraries, a couple of libraries from Google that now support KMP, and then various third-party ones. Important to mention, of course, that there's a ton of other libraries available now as well. And speaking of which, just to highlight how many more KMP libraries there are these days. When I started looking into KMP, as I mentioned, in late 2018, I think there was maybe a handful available at the time. And not only do we have third-party libraries, but likes of Google now porting many of their libraries to work with KMP as well, which is great to see. So the first of the 5 samples we're going to cover is people in space. This was the first dedicated Kotlin Multiplatform sample I created. The functionality in it is quite minimal, shows the list of people in space and the position of the International Space Station. We have Android, Wear OS, and iOS clients, along with Compose for desktop and WASM-based Compose for web clients as shown here, and also a Ktor-based backend in the project. And this is a high-level architecture diagram showing the key moving parts of the project. We're using Jetpack ViewModel in shared code, more about that later in the talk, using Ktor to make HTTP requests to the backend, and SQLDelight then to store the data retrieved in a local database. And that database is used then to what's used to drive the UI. We also have some Compose UI shared code across the platforms. And this section we're going to talk about Coin, Ktor, SQLDelight, and KMP-NativeCoroutines. First library we're going to talk about is Coin. It's the dependency injection framework I use in most of the KMP samples I have. I think it's also probably fair to say that it's currently the most popular DI library used in KMP projects. With Coin, we define our dependencies in a series of modules, module definitions like this. In a KMP project, we typically have one module for common dependencies, as shown here, and then use KMP's expect actual for a module that we define for each platform, as we'll see shortly. And also showing here an example of injecting dependencies using Koin, in this case, injecting the dependencies into the repository class. And these are the platform modules for iOS and Android, for example, using for the SQLDelight database driver and the Ktor HTTP client engine, which need to be defined separately for each platform. And as we'll see shortly, these platform-specific versions of these dependencies will get injected automatically into common code that depends on them. Next up, we're using Ktor for making remote HTTP requests to the backend. Ktor includes libraries for both the client and server, but we'll be focusing on the client here. But there are, by the way, Ktor-based backends in a number of the samples if folks are interested in taking a look. And this is some of the initial plumbing we create to allow using Ktor. We're using Kotlin serialization library, so we just need to configure that so it can be used, for example, for deserializing the JSON we get back to Kotlin data classes. That JSON instance is automatically passed into the create HTTP client method shown here, along with the client engine we showed earlier. Note again, this is common code, but then appropriate platform-specific version of that engine will get injected. Here we see again the Android and iOS specific versions of the Ktor engine being created in Koin platform-specific modules. Okay, so showing here the data classes for the list of people and also for the position of the International Space Station. The JSON returned from the backend will automatically be deserialized into these classes by the Kotlin serialization library as mentioned. And then two methods, fetch people and fetch ISS position for the API class that use Ktor to make requests to the backend. And again, we're using Koin here to inject the HTTP client object into the people in space API class. Okay, now that we've got our data from the back end, we need to store it locally on the device. And for that, we use the SQLDelight library. This works by generating type-safe Kotlin code from a series of SQL statements. And these are the SQL statements for the people in space sample. We have a statement for querying the table, and one's for inserting, selecting, and deleting data. And note that the names shown above the statements are what are using Kotlin code generated, as we'll see next. We can now use the generated code to store the data we retrieved from our backend into a local database. We create a transaction here, and within that, in this example, we delete existing data and store the new ones. And note again that delete all and insert item were generated based on what we defined in our SQL file. And here we use the generated select all to retrieve the data from the backend and expose as a Kotlin flow, which we'll use to drive our UI. We also use this mapper here to convert the result of the query into a Kotlin data class. And just a very small example from the project of a SQLDelight database migration as well. As an aside, the endpoint I used to get the data doesn't include this info. So I ended up creating a Ktor backend that proxies the request and augments the result with additional data. So I've had to add these to the database as well. That backend, by the way, is in the repo if folks are interested in taking a look at some point. One other library I want to highlight for this sample is KMP-NativeCoroutines. And it's one I use in a number of the other samples as well. It supports mapping Kotlin coroutines to a range of different Swift concurrency frameworks. But these days I'm using it primarily for mapping to new structured concurrency capabilities that were introduced in Swift 5.5. Showing an example here from People in Space, where we have a Kotlin method in shared code that returns a flow representing the position of the International Space Station. And then in Swift, we use for-await to observe the data. For-await being effectively equivalent to collect in Kotlin. And note that if this is cancelled in Swift, then that cancellation gets propagated to the Kotlin flow as well. We can also use KMP-NativeCoroutines to seamlessly invoke Kotlin suspend functions using Swift's await. The next example we're using is Confetti. This is a Kotlin Multiplatform project for showing information for a range of conferences. For example, DroidCon Lisbon. It includes various clients, along with the GraphQL backend, thanks to Martin Bonin. Here we have the iOS, Android, and also a Wear OS 1, which was created by Yuri Shimka, who, by the way, also contributed Wear OS clients to a number of the other samples as well. It has a Compose for Desktop client, and also a WASM-based Compose for Web 1 as well, as shown here. And even has Android automated support thanks to Carlos Mota. And again, showing the high-level architecture. Key thing here is the use of Decompose components and using Apollo to interact with the GraphQL backend. We'll talk about both shortly. We're also sharing some of the Compose code across the clients in this project. By the way, just another quick show of hands. Anyone here using Decompose? Okay, one, I think, two maybe. How many people using GraphQL? Okay, not several. And I think it's probably, at least in the Kotlin world, Apollo is probably the standard approach that people are using for interacting with GraphQL backends. And showing an example of this section of, as mentioned, Apollo Kotlin, Decompose, multi-platform settings, and Coil. As mentioned, the clients in this project interact with the GraphQL backend, and for that we're using the Apollo Kotlin library. It's described as a strongly typed caching client that automatically generates APIs from our GraphQL queries and backend schema. The caching aspect of this is very important as well, giving us effectively an all-in-one solution for both retrieving the data from the backend and storing it locally. To use it, we need to initially create this Apollo client object to make various requests. And this is an example of how this can be done. We provide, in this case, a URL, a header containing the conference name, and details of both the in-memory and persistence cache we'll be using. And showing a few examples of its usage. Firstly, for retrieving the list of conferences. Shown here is the GraphQL query that this is based on, and then use of the Kotlin code that Apollo generated to execute the query. The conference data class reference here is also generated by Apollo based on what we specified in the query. And then this is what's known as a GraphQL mutation, where we update data in the back end, in this case adding a bookmark for a session. And again, we make use of the Apollo generated code to perform that mutation. Next up is Decompose. This is a library based on the idea of breaking our code into a tree of lifecycle-aware components that contain observable state, have routing navigation functionality, and into which we can plug our UI. These are most of the Decompose components used in the Confetti project. We see, for example, ones for the list of conferences, session info for a particular conference, speakers, bookmarks, venue info, etc. And if we focus in, for example, on these particular components, these are the set of components associated with the screens we can navigate to from the home screen shown here, corresponding to a tab shown at the bottom, sessions, speakers, bookmarks, and venue. And the key thing here is that the components themselves know nothing about the UI. We just hook up particular UI screens to the appropriate component. We start by showing the set of children defined for home component. We'll explore a little in the next few slides, example of how we'd navigate to the speaker's child and associated UI. So if we drill into a somewhat condensed version of home component, this is the Decompose component, which, as we mentioned, is associated with the home screen in our app. First important concept here is the child stack. It's described as a navigation model for managing a stack of components. The UI, as we see shortly, will observe the current active child in the stack and use that to decide what to show. The child stack is also passed a factory that's used to create child components, which we'll show next. This is the child factory mentioned, and it's used, as the name suggests, to create particular children given a configuration passed to it. For example, config.speakers maps to child.speakers, which in turn wraps an instance of speakers component. We also see an example of how we'd navigate to that child in this on-speaker tab click method that's invoked from the UI. That navigation.bring-to-front is passed the config.speakers configuration, which, as we saw, will map to child.speakers, which then becomes the active child. And this is how, in this example, we decide when to show that speaker's UI. In this case, firstly, in the Compose client. We observe the active child instance from the component stack we saw earlier, see that it's set to child.speakers, as we saw in the previous slide, and then navigate to that screen, passing, importantly, the associated child component as well. An almost identical code in the iOS SwiftUI client, for example, again observing the component stack to decide which view to show. Next up is multi-platform settings library, designed to allow persisting key value data in KMP projects. So this is an excerpt from the Confetti project, where we're storing the name of the conference the user selected. If that value is set, then we bypass the conference list screen next time the app is launched. And we're also observing that setting as a Kotlin flow. The flow setting type of the settings parameter is an abstraction from the multi-platform settings library. And again, we use platform-specific code then to create the appropriate implementation of that. These are part of the Koin platform module definitions for Android and iOS, for example, using DataStore settings as the implementation on Android, and NS user default settings on iOS. The last library I'm going to show for this sample is Coil, one that folks might be familiar with from Android. It provides image loading, rendering functionality, and now also supports Compose Multiplatform. And this is a small example of it being used to show profile images in the session detail screen in Confetti. In this case, in shared Compose Multiplatform code that's also been consumed in the iOS client as shown here. Next KMP sample is bike share. This shows the list of bike share networks for particular countries and bike availability info for each network. Again, we have Android and iOS clients. We also have a Compose for desktop client, and as shown here, a WASM-based Compose for Web 1 as well. In this case, we're using the KMP-ObservableViewModel library for our shared view models, using Ktor to retrieve the data from the back end, and then persisting it locally using the Realm Kotlin library. And we've been talking in this section about Realm, KMP-ObservableViewModel, and also a plugin for generating Swift packages from shared KMP code. First library we're going to talk about is Realm Kotlin. Just another quick show of hands. Anyone here using Realm? Okay, 4 or 5. As described in the documentation, it makes persisting, querying, and syncing data as simple as working with objects in your database. The first thing we need to do is create a Realm instance, which we'll use to interact with the database. We pass it the object types we're going to be working with, in this case, just the one representing a bike network. And this is that bike network object, used, for example, for displaying the information shown on this screen on various platforms. Now, by subclassing Realm object like this, we're able to directly persist this object to the database. And here's an example of code to iterate over the list of networks we got from the back end and write them to the database, using realm.write to create a transaction, and then copy to Realm to actually persist the object as shown here. And a small example then of code then to read those network objects from the database, returning a flow which again we can use to drive our UI. Next up is KMP-ObservableViewModel. This is the library that up to a few months ago was known as KMP-ViewModel. It's now described as a library to use Android X Kotlin view models from SwiftUI. Key aspect of what it offers is ability to expose Kotlin state flows, for example, as Swift properties that can be directly observed in SwiftUI, as we'll see shortly. This is an example of one of the shared view models in the bike share project, in this case exposing the list of countries we're displaying. We're using our repository class to get the list of countries, doing some transformation of that information, and exposing then as a Kotlin flow. And this is how that's consumed in SwiftUI in the iOS client. We instantiate the view model we saw in the previous slide using the add-state view model property wrapper provided by the KMP-ObservableViewModel library, which then allows that country list state flow from the view model to be observed directly here as a Swift property, which is very powerful. And this is the Compose equivalent. Here we observe the state flow as normal, using, for example, collect a state, as shown here, though that should probably be collect a state with lifecycle, I just realized. As with the SwiftUI client, any change to country list will cause the UI to be recomposed. Next up is a Gradle plugin that generates a Swift package from shared code, which can then be easily consumed in Xcode. Another quick show of hands. Those people using KMP, how many people are using Swift packages? Exposing their, okay, very good. It's an interesting model in terms of how you how you package KMP code and make it available to your iOS developers, so that in many cases maybe they don't know it's KMP code, which is sort of not a bad result sometimes. This is an example of the associated build config for the bike share project. Here we're targeting the iOS and macOS platforms. In this case, the output of that plugin is published to a separate GitHub repository, but that could also be done in the same repo. In this repo, by the way, we're including samples of SwiftUI code. You can use them to consume the Swift package, as we'll see next. And a small recording then showing how to add a Swift package to an iOS project in Xcode. We start with a new iOS project. We then copy the URL of the GitHub repository containing the package, and then use that to add a package in Xcode. Lastly, we copy the sample SwiftUI code from that repo README and paste it in, and we're ready to go. Wanted here to also show just how easy it is, in general, to consume a Swift package containing shared KMP code like this. And what's shown here is the same regardless of what that package or how that package is created. And we see here the super basic iOS app showing the list of bike networks. And by the way, another more recent and much more comprehensive approach you can use for creating such packages is Cambridge, which I definitely recommend folks taking a look at. It takes care of both producing the package and publishing it, and also provides capabilities for local development as well. It's an approach I've actually started to explore using in the Confetti project. Okay, the second last sample we're going to use today is Climate Trace. This displays per sector emission information for different countries. Again, we have an iOS and Android client, and also a Compose for desktop and WASM-based Compose for web ones as shown here. In this project, we're using the KMP-ObservableViewModel library to share our view models. In this case, actually using Molecule to create our UI states. Okay, one last call for the audience participation. How many people using Molecule? Okay, Ed again. We're using Ktor to connect to the back end and Ktor to persist the data locally. And this sample is also using Compose UI code across the clients. And as here we'll be talking about Voyager, Molecule, window size class, Compose on iOS, and Jetpack navigation. So first up, Voyager. This is primarily a navigation library that works across a range of Compose multi-platform clients. It supports a wide range of functionality, including different navigation types, state restoration, transitions, lifecycle callbacks, backpress handling, and deep link support, along with integration with a number of other frameworks. It works on the basis of having our Compose code contained in these screen classes. This is an example from Climate Trace of the screen showing the list of countries. And we see then use of Voyager's navigator.push when an entry is selected in that country list, causing us to navigate to the country emission screen, passing in the country object. And this is an exit from that country emission screen. We can see here there in use of Voyager's navigator.pop to navigate back to the previous screen. Next library we're using in the sample is Molecule. It's described simply as a way to build a state flow or flow using Compose. We're talking here about Compose runtime here rather than Compose UI. This is typically done as part of, say, a view model to create observable UI state, with that implementation then very strongly encouraging a unidirectional data flow type approach. So this is part of what we have then inside our view model in the Climate Trace sample. In this case being used to expose UI state for emission information for a particular country. Key thing here is this call to launch Molecule to create the state flow representing our view state. And it does this by using the country details presenter composable, which we'll show next. We also define the events, mutable shared flow, representing the events that the view model will handle. And this is part of the country details presenter composable. Here we have some composable state. Any changes will cause country details presenter to recompose. In the launch effect, we collect the events we mentioned in the previous slide and set certain state based on those. For example, the country or the year that the data is for. And here we react to that country or year state being changed to make a number of requests to our repository, the results of which then are used to create our UI state, which will be returned from the composable. So quite a different approach and requires different mindset, but definitely an interesting option, and one that I think maybe becomes a bit more applicable as the number of data sources we're using to create our UI state increases. Another Compose multi-platform library we're using in this KMP port is this KMP port from Chris Bain of Android's Material 3 window size class. This allows creating adaptive UIs based on a set of window size breakpoints that we can generally apply across our clients. In this example of different layouts, we dynamically show depending on the screen size, showing list and details in a column on the left, and then showing in a row as the window is resized. And we see this in action here as well. These particular layout configurations are, of course, just one example. Another common approach is to switch between list detail and a list as the window gets smaller. Just a small aside, if people are using Compose multi-platform, if you're tracking the I guess, pre-release of the 1.7. 1.7 beta came out, I think, this morning or last night. This is actually provided, included as part of the offering. This third-party library is no longer needed, but the API is effectively the same in both cases. And this is a distilled version of some of the code used. The specific layouts aren't too important. Key thing here is how we're querying for the window size class in shared UI code and showing different layouts depending on what it's set to. And the UI will get recomposed then whenever a change causes the width or height of the window to cross a breakpoint. Next thing I want to show here, also from the Climate Trace project, is a small example of shared compose UI code being consumed on iOS. We have, for example, this function exposed from our iOS main code in our KMP module. It uses Compose Multiplatform's Compose UI View Controller, which in turn includes the country list view composable function, which is in shared common code. And then on iOS, we take advantage of the ability to include a view controller in SwiftUI code. Here we define such a view controller, this country list view shared struct. And that in turn invokes the shared compose country list view controller we showed in the previous slide. Here we also pass a callback that's invoked when the country is selected in that list. And I'm using this approach in several of the samples. Lastly, for this project, Jetpack navigation. We're using a version of the library that was included in a recent Compose Multiplatform beta and expanded on in subsequent versions. This shows some changes that were added to Climate Trace to try it out, available in the branch if people are interested in taking a look. Same code as we'd use, for example, in an Android app, but this time it's shared Kotlin Multiplatform code. And another aside here, by the way, I guess Android developers probably have tracked that you can use strongly typed approach with the navigation library in Android, and that's now available in Compose Multiplatform as well. In this example, still, we define a number of routes which we can navigate to, for example, the list of countries and details for a particular country. So this is a nice capability to have now, and one more thing that makes migration from existing Android apps much easier. We'll talk more about various other Jetpack libraries that now support KMP in the next section. Okay, we're nearly there. Next up is Fantasy Premier League, the last of the KMP samples we're covering today. The project displays information for a competition for the main football league in England. These are screenshots, again, for the Android and iOS clients. And this is the Compose for desktop client. So in this project, we're retrieving the data from the backend, again using Ktor, storing locally using Jetpack Room, thanks to its new KMP support. We're also using shared view models, but in this case, we're using the recently announced version of the Jetpack ViewModel library that now supports KMP. And also using shared Compose UI code. In this case, for the player details screen, we'll see shortly. In this section, we're going to talk a little about the use of the aforementioned Jetpack ViewModel, Jetpack Room, Jetpack DataStore, SKIE, and KoalaPlot libraries. So as you probably gathered, this project has sort of become my designated Jetpack KMP sample. As you can see here, we've rapidly got to a point where several key Jetpack libraries are now available to be used in shared Kotlin multiplatform code. And I think this is something that has really excited the dev community. Now, as I said before, whether these libraries are the best solution for a particular functionality they provide is a different story, given the options we now have in the KMP world. But key thing is that having them provides, as I said before, a very nice migration path for existing Android apps. One library actually that I'd forgotten to include in that tweet in the previous slide was Jetpack Paging, which actually had its first stable release recently as well. And this is used, by the way, in the Morty KMP samples I have. So first of these Jetpack libraries is ViewModel, again one that will be very familiar to most Android devs. Used as part of a general MVVM pattern, its role is primarily as a holder of observable UI state and as a conduit of actions that would typically affect that state. The Jetpack version has had some additional responsibilities in the Android world around the caching of state through configuration changes and as part of navigation graph, etc. With the KMP support now, and importantly also that of the lifecycle library, this is now being generalized to work on other platforms as well. So this is a small example from the project. It looks like a standard Android view model that many of us have used in Android apps before. Difference here that this is defined in shared common Kotlin multiplatform code. We'll talk shortly, by the way, about how we're using the SKIE library to access that state flow in SwiftUI code. Next library we're going to talk about is Jetpack Room. It provides, as described here, an abstraction layer over SQLDelight. And this is one of the entities from the project that we're going to persist. In this case, for information about a particular player. Just a standard Kotlin data class marked with @entity annotation. We then have this abstract class in common code representing the database. And that's also used to access our data access object. We're also providing here the list of entities we're working with. A SQLDelight database table would be created for each of those. And as we've done elsewhere, we use KMP's expect actual mechanism to create platform-specific implementation of that database class. And this is the data access object we referred to in the previous slide. Here we define various database queries we'll be making, showing just the ones related to a player here. We have methods for inserting the list of players, returning the players in the DB as a Kotlin flow, and also retrieving a particular player by ID. And it's this data class, or this class rather, that we'll be using in our repository. And showing excerpt from that repository class here, we inject the app database instance using Coin, and then use it to get the data access object, which we use then to write info to the database. And also expose what's in the player table in the database as a flow, along with the method to get the particular player by ID. So next up is Jetpack DataStore. Similar to the ViewModel, it's another Jetpack library that now supports KMP. It's been available in pre-release versions for a while, but went stable again relatively recently. It supports storing key value information, as well as typed objects using protocol buffers. This sample had in fact been using the multi-platform settings library that we saw earlier, but it was recently migrated to use DataStore directly. And this example is being used to store the particular fantasy leagues a user is part of. The DataStore object is injected into the constructor, again by Coin, with implementation again being created in platform-specific modules. We have methods to update the list of leagues, and also to return the list as a flow, which can be observed. And this is what we have in the platform module for Android. Specific details are not too important, but just to show again how, as we've seen a few times, KMP's expect actual mechanism in conjunction with Coin allow us to easily plug in platform-specific code like this. And similarly then for iOS, again, we won't focus too much on the specific details of how that DataStore method is implemented. Next library we're going to talk about from this project is SKIE from TouchLab. SKIE stands for Swift Kotlin Interop Enhancer. And supports a range of functionality as mentioned here. We'll show how we're using some of these features in this project, specifically the coroutines flow and sealed classes support. First up, invoking Kotlin suspend function from Swift. We have this getEventStatus suspend function in shared Kotlin code. And we're able to use Swift's await to invoke it then in our iOS client, thanks to SKIE. And likewise for flows. We have that player list UI state flow in our ViewModel, which we can then use Swift's for-await to observe that in the iOS client, in a Swift UI task view modifier in this case. That Swift for-await, as mentioned before, is analogous to Kotlin's collect. And as with KMP-NativeCoroutines, when the Swift UI screen that's used in is no longer shown, then this is cancelled and that cancellation is propagated to the Kotlin flow. Another area where there's a disconnect between Kotlin and Swift is sealed classes, and this is something SKIE also addresses. We have this player list UI state sealed class that's being emitted from our ViewModel, as we saw before. SKIE then provides a way to exhaustively switch over the sealed class hierarchy by generating a Swift enum that wraps the Kotlin sealed class. And we see an example here in Xcode where it reports this switch must be exhaustive error then if any of the cases are missing. I mentioned we were sharing Compose UI code for the player details screen across the clients. That screen shows a graph, and we're using the KoalaPlot CMP library to show that. It supports a wide range of different chart types, but we're using it in this project for a standard bar chart, as we'll see next. And this is the somewhat condensed version of the code then to show that chart. Key thing again is that this is shared Compose UI multi-platform code that we use for all the clients. For example, in the iOS client shown here. Okay, so that was a whirlwind tour of many of the Kotlin and Compose libraries used in various KMP samples I'm involved in. Shown here again the ones we covered today, broken down by function. We have libraries, for example, for persistence, remote API requests, dependency injection, ViewModel component sharing, navigation, Swift Kotlin interop, packaging, and some Compose UI multi-platform libraries as well. Hopefully you got at least a flavor of the capabilities these libraries provide and how they can be used. As mentioned, I'll make the slides available, so they hopefully act as somewhat of a reference from the material we covered here today. Thank you.